Hello, this presentation will be about Covercrypt for construction for efficient quantum-safe hybrid key exchanges with hidden access policies. This is work by Théophile Brézot, a developer at Cosmian, David Pointcheval, my PhD advisor at the ENS of Paris, and myself, Paola de Perthuis. And I am working both at Cosmian and at the ENS of Paris. This is, so you can find more detail in the full version on ePrint 2023 836. And so this work is being published at ESORICS 2023. Now, let me recall why key encapsulation mechanisms in general are useful and how they work. So basically, here you will send out an encapsulation from which someone can derive a key if the encapsulation was done. So this is the usual setting with a public key for which they have the secret key. And if they have the corresponding secret key, then they can derive the key you wanted to transmit, and that you also got out from the encapsulation on your side, even if you don't have the corresponding secret key. Key encapsulation mechanisms can be used to get public key encryption in a very efficient way, in which you combine public key cryptography with symmetric key cryptography to get the best of both worlds. So you will want to use a symmetric key for your communications because then your ciphertext can be of minimal size. But you would like to send out the key for communications to someone in particular and not to anyone. So you will want to send it out with respect to someone's public key for which they have the secret key. And that's how it can be used. So you derive the first key, and this symmetric key will be later on used in the KEM paradigm for your communications. It can also be used in less classical contexts, and when this was a use case for telecommunications, in which you would sometimes like users to be able to connect to services without sending out requests that might identify them. So the service would broadcast encapsulations with respect to some public keys, so for user attributes, for instance, and all those users who, with fitting attributes, would be able to get a session key and connect to the service without having had to send out requests first. Now that I've motivated this work, let me talk about a few interesting properties we wanted in this work. And one of the first ones is to have post-quantum resistance. This is more and more usual security level that we want. But we also wanted to hybridize post-quantum schemes with well-known classical ones, so that the security, here the privacy of the encapsulated keys, relies on the best of both securities. And this is a recommendation from several security agencies, standards organizations, so that we don't transfer all our communications directly and using new problems without keeping the old one for some time before we really get a hang of the security of the new ones over the years. And to do this, one basic way to do it, so if we want to hybridize two schemes, so here the beaver has two secret keys corresponding to both schemes, and the rabbit will encapsulate keys with respect to both these keys, public keys. Then the beaver can decapsulate these encapsulations. And one way to do this is to take a XOR of both derived keys and use this XORed key for communications. Another interesting property is anonymity. We would like the encapsulation policies, meaning who these keys were encapsulated for, to remain hidden for people who are not the recipients of the encapsulations. Meaning that if the frog here receives an encapsulation that was not intended for any of frog's keys, and the frog tries to decapsulate the key or do anything about anything with the encapsulation, they can't make out anything about who this encapsulation was meant for. And it looks like an encapsulation for any other public key for which they do not have the secret key. And now we'll get to the core of one of the main features we have in this work, which is that usually in a system with many users, you want to share some data over groups of users and not just one individual in particular. And these groups correspond to some attributes that the users have. So you might want to encapsulate to communicate with all the users who are in a particular department, for instance. And you would like to provide encapsulations with respect to attributes rather than user identities, so you don't have to send out many encapsulations just for one purpose. Now, the usual way to do this in the literature is to build a KEM using attribute-based encryption, or ABE for short, in which users will have attributes, secret keys corresponding to each of their attributes. And here the rabbit will be able to encapsulate with respect to any policy, which will be a logical formula on the set of attributes, and to encapsulate for all the users who have attributes who fulfill this logical formula on the attributes. This can be done, but in practice, it's very inefficient. And also, usually you do not need to use every possible logical combination of the attributes for your encapsulation. So there are actually much more efficient things we can do, because this is quite heavy just for pre-quantum security, and for post-quantum one, it's even worse. So in our work, we use subset covers of attributes in which we define several axes of attributes. So one axis could be the user's countries, or the user's hierarchy level, or the user's department, whatever. The users can have several attributes along that axis, and you will give them keys for all the intersections of attributes they have between the axes. And in this way, we can build something really efficient. So here is just an example of how it works. So if the rabbit here wants to encapsulate for aquatic users, the users fulfilling this policy will be the frog and the beaver. They both have a key for the key for aquatic users. The rabbit encapsulates with respect to that key, broadcasts the encapsulation, and all the users will decapsulate. And for the intended users, they will get the key that the rabbit transmitted, and the other ones will just get some random key. Now, we would like users who are decapsulating something random to be aware of it and to be aware that their decapsulation was not a success. And for this, we build a property which we call authentication. And let me show you how it works. So the rabbit first makes a usual encapsulation, but from the derived key that the rabbit also gets when encapsulating, the rabbit applies a pseudo random generator on that first derived key, from which they derive a key and a tag. And this key is actually the one that's going to be sent out and used for communications. And the rabbit sends the first encapsulation with a tag. Then all the users decapsulate and apply the pseudo random generator on the decapsulated keys. And from these, they get keys and tags. And then they compare the tag with the tag that was sent out. And if it's the same, they know that their decapsulation was a success and that they obtained the key that they needed to get. And else, if it's not, they know that they just got some random stuff, meaningless stuff from the decapsulation. Now, this authentication property that we built also boosts efficiency. Let me show you how. So in the subset cover of attributes, a user can encapsulate with respect to a policy that has logical ORs inside of it. And with all the ORs, you have a corresponding attributes that are ORed or intersections of attributes. And each of these will correspond to a key with respect to which the user encapsulates. And then they will send out all these concatenations of encapsulations for all the combinations that are ordered in the policy that all encapsulate the same key. And this is sent out, and then users try out their keys on all the encapsulations. And with the authentication, they can know whether that worked or not. That's very useful because they can stop when they have a success because they know that all the keys encapsulated are the same ones, and they don't have to go through all the procedure. And also they know which what is random stuff that they can just discard and what is relevant to their communications. Then one aspect of what I've just presented is that users have keys which correspond to attributes or intersections of attributes or combinations of attributes. And ideally, we would not like users to share the same keys because that's generally not good practice. If someone leaks their keys, you would like to know who did it. So what we offer here is to also give users a unique user key that they use in the decapsulation procedure and that they're required to use, but so for one same encapsulation for one attribute, the user has to use their unique user key. And from this, we also have a tracing mode that we detail in our work. Yeah. Now I will also talk in a bit more detail about the hybridization of two KEMs that I mentioned earlier, because what we saw is that we actually have concatenations of encapsulations when there's a policy with an OR and several combinations of attributes. And we would like the same key to be encapsulated in all of these. So, but usually we don't really control what key is going to be derived when doing the encapsulation. So here is how it works. So when hybridizing the chems, so here I have, for each block, I have 2 chems. So I actually have 2 encapsulations, and each encapsulation gives me a derived key. And now for each block, I also send out a XOR of these derived keys with the session key I actually want to encapsulate, so that deriving the keys, one can get to the session key I want it to communicate. And now here is how we can optimize things a bit when we have a public key encryption scheme in one of the chems. Because in this case, you can really control the key that you're encapsulating. So in the first chem, you do as usual. You get your derived key, and then the second one, you encapsulate this derived key from the first chem with the session key, and from this, you win a bit on the communication. Also, as a side note, but you can find more detail in our paper. For the top pre-quantum scheme, we used ELGAMAL, and in this scheme, we can actually get 1 encapsulation for all the attributes. So we can reduce sizes even more. Now about performance. So Théophile did an implementation of this scheme in Rust, and it's very efficient. So let me show you, just to give you an idea, a few numbers. We compare the times for encapsulation, decapsulation between our scheme, Covercrypt, and GPSW-based chem. So GPSW is the usual scheme you would implement for attribute-based encryption. This is a pre-quantum scheme. Ours is also post-quantum, but we still get an order of magnitude in times. So that's pretty good. And now to conclude, so we built a chem with hybridization to get both post and pre-quantum resistance, anonymity, subset covers of user attributes, and it's quite efficient. And also users have unique user keys. So thank you, and if you have any questions, let me know. Thank you. Also, you can find the full version of our work on ePrint, and this work is published at ESORICS 2023.